Hey there, astronomy students. This is Miss Ruark. 14.2. We're going to talk about black holes, everybody's fave. Alright, so black holes. What is a black hole? Well, let's find that out. Alright, when neutron stars happen, there's a mass limit for them, just like there is for a white dwarf. Remember, white dwarf mass limit is 1.4 solar masses, right? The Chandrasekhar limit. Well, the white dwarf, or excuse me, the black neutron stars, if it gets to a mass, if it collapses and gets to a mass that's greater than 3 solar masses, the degenerate neutrons can't stop the contraction, and it contracts to an extremely small size, perhaps even to a singularity or an object with 0 radius. The gravity that's going to be around this thing is so strong that not even light can escape it, and we call it a black hole. Ooh. Alright, so let's talk about escape velocity from first semester. Alright, so escape velocity that's needed to escape the gravitational pull of an object, right? It decreases with distance. So escape velocity from the surface of the Earth is approximately about 11.6 kilometers per second. But because it decreases with distance, if we start, let's say, in the atmosphere, the escape velocity will be much lower. If we were to happen to take the Earth and compress it into a smaller size, the escape velocity we would need to escape from the surface would be higher, because we would take that same mass, put it into a smaller volume, which means the density of the Earth would be higher, which gives us a greater gravitational force. All right, there is a limiting radius where the escape velocity reaches the speed of light, which is the boundary of a black hole. So if we were to take that and compress the size of something extremely small and down into this teeny tiny little surface with all the mass inside of it, it would have a greater gravitational pull, and we would have to have more escape velocity to get away from it. All right, so the radius that this limiting radius, or the radius of the boundary of a black hole, is what we call the Schwarzschild radius. And for a black hole that's only a few solar masses in size, the radius would be a few kilometers. Now, if the black hole was larger in size, of course, the radius would be larger, right? Okay. So the Schwarzschild radius and event horizon. There's no way to detect what's happening inside the Schwarzschild radius, and it's referred to as the event horizon. So once something goes into or past the event horizon and into the black hole, we can't find out what's going on inside of it. So nothing can escape, because the speed of light, nothing can go faster than the speed of light, and since black holes suck up the speed of light, well, yeah, we're screwed. Okay, so Schwarzschild radius, just to give you an idea of what they're like, the Earth has a mass of about a teeny tiny solar mass, and our radius would be 0.9 centimeters. That's teeny, right? So the sun with one solar mass has a radius of 3 kilometers. A star with 2 solar masses would have a Schwarzschild radius of 6 kilometers. But look at this, the 10 solar mass one would have a radius of 30 kilometers. Okay, so the bigger the mass, the bigger the radius would become. All right, they do believe that supernova remnants that have no pulsar or neutron star in them may contain black holes inside of them. Ooh. Okay, we don't know them. All right, once matter falls into a black hole, guess what? It loses all of its properties. And how do we find a black hole? Well, by the properties that they don't lose. So the 3 quantities or properties would be mass, electrical charge, and angular momentum. Okay, if you were to look at a black hole, or to look at a black hole, we use Einstein's theory of relativity, the general one, and we say that at a distance, gravitational fields of black holes and a star of the same mass will appear identical. However, if you go closer to it, so you decrease that distance, you'll be able to see that there's a deeper gravitational potential between those two. Okay, so you'll be able to observe that the closer you get to it. Also, if an astronomer, an astronaut, or anything starts to go towards that black hole, descends down towards it, gets closer to the event horizon, they'll be stretched vertically and squeezed laterally, which means they'll be lengthened and thinned, and they call this the spaghettification effect. Haha, you like that one? I know. All right. Another thing that you'll notice that happens is time dilation. So as you get closer and closer to a black hole, the clocks, let's say we start every single one of them at 12 o'clock, after 3 hours, the observer far away here will notice that it is now 3 o'clock. Well, guess what happens? If you get closer and closer to the black hole, the clocks will run slower and slower. So after 3 hours, it doesn't look like much time has changed because things are now moving at the speed of light. And this one here, go back. The time dilation, or the difference in time, becomes infinite. It just pretty much goes away at the event horizon, so on the boundary of the black hole. Gravitational redshift will also happen. So all wavelengths of emission near the event horizon, or the boundary, will be stretched and redshifted. Okay, so the frequencies will actually be lowered. Okay, so how do we observe black holes? Since no light can escape a black hole, we cannot observe them directly. So how do we observe them? We look for binary star systems where mass flows into a compact object and it gives off X-rays. If the mass of a compact object is greater than 3 solar masses, the object cannot be a neutron star and is probably a black hole. And guess what? Many of those objects have been identified. How do we know? Well, look here. Candidates for black holes. Okay, check out that right there. Remember, it has to have a solar mass of 3 or greater. Oh, that's a lot. Okay, yeah. All right, so compact objects with disks and jets. Okay, black holes and neutron stars, of course, can be part of a binary system. We've said that already. All right, so what happens? Accretion disks can form when matter is pulled off of its buddy star and forms around the black hole or the neutron star. And this matter, in the form of the accretion disk, can heat up to a few million Kelvin, and it's a strong source of X-rays. All right, so what happens with this? Well, we get this thing called an X-ray burster. Okay, so remember when we had the white dwarf would pull the fuel off of its companion or its buddy star, and so you would have hydrogen all around the white dwarf, and it would eventually raise the temperature and ignite and give off radio burst or radio blast, right? Well, same thing's happening here with these X-ray bursters. Okay, so we've got this binary system in which the mass transfer puts all of this matter on the surface of a neutron star, and then the helium will fuse or ignite into fusion, and the surface explodes. And when it explodes, it gives off a burst of X-rays. And you'll notice that as it explodes, it bursts off. All these X-rays are given off. It's accumulating, gives off more. Accumulates, it gives off more. It accumulates, it gives off more. Okay. The rapid outburst is going to be followed by a gradual decay, so it's got to have time to just kind of, chill out. And repeated outbursts, the longer the interval between the bursts, the stronger the burst was. Okay? All right. Let's see. There was one that happened. Here is an optical picture of an X-ray burster, and then this one here would be the ultraviolet, so you're able to see the UV. Now, it would have been nice had they shown it in a different way, but that's okay. All right, black hole binaries versus neutron star binaries. Astronomers can observe rapid flickering called quasi-periodic oscillations, and these are produced by blobs of gas that orbit very rapidly and spiral inward in the accretion disk. So you notice here, the accretion disk, right, they're going around, and some of this matter is going more and more in towards the center. Okay, so you can observe this happening. Well, you can tell if it's got a neutron star in the middle of it or if it's got a black hole in the middle of it. And the way you can tell is that if the accretion matter or the accreted matter disappears, it's a black hole. If the accreted matter produces an X-ray flash as it impacts the surface of whatever's on the inside, it has to be a neutron star on the inside. Okay. Accretion disks around black holes are going to be strong X-ray sources, strong sources of X-ray. They rapidly and erratically are variable with flickering. Okay. Sometimes they're quasi-periodic oscillations, and sometimes they're radio-emitting jets. Yeah, they're weird, right? And then rapidly spinning accretion disks around neutron stars or black holes can actually twist magnetic fields into tubes and eject narrow, powerful jets of radiation and matter. Now, that would be what this is right here. It's giving off all this stuff, and it's line shifting and blah, blah, blah. The problem is they don't fully understand this yet. So they're still doing research into it. You could be a researcher for it. Oh, yeah. Okay, moving on. Gamma ray bursts. These are short bursts of gamma rays. They appear to be related to violent events involving neutron stars and black holes. Soft gamma ray repeaters are thought to be related to disruptions in the crust of magnetars and may occur. Yeah, here's a host galaxy. All right. They may occur during hypernova, which is a supernova-like explosion of a massive star that collapses directly into a black hole. Some could be caused by the merger of two neutron stars, but it's not confirmed yet by direct observation. All right, and then, to leave you with some black hole stuff. And I'll see you in class.